Dr. Muhammad, and I am going to talk about the Euler's differential equation in this video. And let's go and have an introduction for this. So for today we are going to talk about a special shape or form of the differential equation. It is going to be based on Euler's form or Euler's formula. And we are, as we said many times, whenever that we have a certain form for the differential equation, this tells us how to solve it. So let's go and see what is the form of Euler's differential equation and how we can solve it. Okay. So let's have a definition and let's see what is the form of this Euler equation. First of all, if we have the form, if we are going to say that we have A and B are constants, the second order differential equation shown, which is x squared times y double prime plus ax times y prime plus b times y equal to 0. This is called Euler's equation. This is called Euler equation. Take care here that we have x squared is used and multiplied by the second derivative of y. We have the first constant that we were talking about here. It is here, which is multiplied by the second derivative of y, but we have x as well, is multiplied here. And then at the end we have b, which is the second constant that we were talking about, multiplied by y. And the right hand side is 0. This is the form of it. Okay, so this is the form of this Euler's differential equation. Euler's equation is defined on the half lines x larger than 0 and x smaller than 0. Actually we are, whenever we solve an equation, we are talking about intervals. So actually here, if we are saying that this is 0, for example, and we have the values which is larger than 0, it is here, and the values smaller than 0 is going here. This is, as we said, this is the interval of the solution of our equation. So according to Euler equation, we are going to find the solution. We can solve. We will find solutions for x larger than 0. So for this part, we can find the solution. And a simple adjustment will yield solutions for x smaller than 0. Actually, we are not very interested in x less than 0. We are going to focus on how to find the solution for our case for the x larger than 0. A change of variables, how we are going to solve it. This is the way of how we are going to solve it. We are going to use a technique called change of variables. Changing of variables. A change of variables will convert Euler's equation to a constant coefficient linear second order homogeneous equation. Look at this. It's beautiful that we are going to use a changing of the variable. We are going to change the variable x to another variable, okay? And then after that we are going to find this conversion is going to make or convert our Euler's equation to a constant coefficient linear second order homogeneous equation, which we can always solve, right? It is very common for us, and you have trained well on how that you can solve this constant coefficient linear second order differential equations. So how we can make this conversion, or what is the changing of variables that we are going to use? So let's assume that we're going to change this x to another exponential form to be e to t. So we are going to change x to be e raised to the power t. Or equivalently, we can say that t equals to ln x. t equals to ln x. This is the equivalent to this one. If we substitute x, which is equaling to e to t, into y of x, the main differential equation, we obtain a function of t, because we are going to remove this x here and we are going to put instead of it the new parameter that we have used, right, which is t. Okay, so in this case, which is, that we're going to remove x and we are going to substitute e to the power t. Then we are going to obtain a function which is y uppercase in a new variable called t, and this function actually it equals to the y lowercase, which is related to x, which is e to t, right? So take care of the uppercase and lowercase. Okay, so we are going to change using the conversion of variables the equation from being a function of x is to be a function of t, and we are going to make denote this to be y uppercase, y capital. Okay, and then we are going to solve this equation using constant coefficient method, which is already we have learned how to solve, and then it is going to help us to solve the original equation and obtain the value of the general solution, which is y of x that we are going to have at the end. Let's assume, let's go through this and we are going to understand clearly by taking some examples. So we can prove that actually the derivation of this part, you can find it in the textbook. You can read it for knowledge, for your own knowledge, for information only. It will not come in the exam, just you can understand it by yourself and also for your knowledge. That from the conversion, after we are going to convert x to e to t, and then we're going to substitute in the main equation, we can find that we will end with a constant coefficient equation in t, which is y uppercase double prime t plus a minus 1. What is a? It is the constant that we said before, times y prime of t plus b times y of t, and the right hand side is going to be 0. Okay, there is a derivation for this, but now you can read the constant coefficient differential equation in t directly from the original equation that you have. If you know a and if you know b, then you can put this equation directly. Again, let's go back. This is a, this is b. Take care. A is the coefficient or the parameter or the constant that is multiplying y prime, and b, it is used for y. However, y double prime, there is no constant here. We should always see x squared here. Okay, so take care of the form itself so that it will help you in solving the problems. So now we can read directly our equation or our constant coefficient equation in t. Take care that our variable is t, as you can see here, and the function, we call it uppercase y. Here y double prime, here y prime, here y, but take care it is y. So whenever that we put like y like this, okay, this means that it is a function of t. Whenever that we put small or lowercase y, this means that we are dealing with a function of x. This is only a notation for what is the meaning, the significance of y uppercase and y lowercase. This is a constant coefficient equation. We're talking about this equation, a constant coefficient equation, which we know how to solve. Definitely, we know how to solve it from the previous videos. Solve this transformed equation for y of t. We're going to deal with this equation and we're going to get its general solution, which is y uppercase in terms of the parameter t. Then after that we're going to replace t with ln x. That's it. We're going to replace t with ln x at the end to obtain the solution y lowercase of x. This is the general solution of our main variable, original variable, which is x. Okay, so we're going to solve this constant coefficient to get the general solution in terms of t, the parameter t, and then we're going to replace and substitute t equal to ln x to obtain the solution or the general solution of the original x parameter of the Euler equation. So there are some hints here that we need to recall them so that it will be easy for us to solve such a kind of equation. It is useful to recall that for any number r, if we have any number r, and for x larger than 0, that x raised to r equal to e, the exponential function raised to r ln x. E raised to r ln x. This is common sense, right? But again, we're going to encounter this many times in our problems. So just we recall them and be sure that you are really familiar with it. Another thing, whenever we say that e to ln k, this means that it is k, right? This is for any positive quantity k. This is also common sense, but we are going to use them extensively in our problems. For example, if we have e to 3 ln x, directly it equals to e to ln x to the power 3. Then we're going to remove this and we say that it equals to x cubed. Okay, so this going to be changed directly to this, and you're going to find this transformation is happening frequently in our problem solution approach. Okay, now let's go to the next slide. And I think that we are ready now for the solution of some examples. Let's have the first example. Let's assume that we want to find the general solution of this equation, which is x squared y double prime plus 2x y prime minus 6y equal to 0. If you look here, this really fulfills the condition of Euler's formula. So we have x squared here, and there is no constants. There is y double prime plus 2, which is a constant, times x times y prime here, minus a constant times y. So we have a, we have b, right hand side is 0, then this is an Euler differential equation. Okay, so we are going to have a to the constant equal to 2, b equal to minus 6. This Euler equation transformed to directly, we can put our equation directly without any problem. So we're going to put it as y double prime of t, take care of the capital and t here, plus y prime of t. Then here it is 1, as if there is 1 here, because it is supposed to be a minus 1, which is 2 minus 1, right, which is 1 here, so already removed, minus 6, which is b, and this is b times y, and it equals to 0. Okay, so now we have our equation and we can solve it easily. This is a constant coefficient linear homogeneous equation, and it has the general solution. If you look to this equation, we're going to find that the characteristic equation can be solved in terms of lambda, and we are going to find real distinct roots. So please solve it by yourself, okay, and get lambda 1 and lambda 2, okay, and you are going to find that lambda 1 equal to minus 3, lambda 2 equal to 2. So we are dealing with real distinct case here, which is case number 1, if you remember what we have explained before. This constant coefficient linear homogeneous equation has the general solution based on the characteristic equation having two roots, real distinct roots, -3 and 2, and we can put it in this form. Y capital of the parameter t, c1 times e to -3t plus c2 e to 2t, right? We have -3 and 2, -3 and 2 for our roots, real distinct roots. And this is the equation. Now let's go to, remember that this is function in what? It is function in t. Still we didn't go to our final destination, which is we want to have the general solution for x, not t. So now replace t with ln x. Replace t with ln x to obtain the general solution of our Euler equation. So we are going to put this equation again. We're going to rewrite again here. So we're going to say, instead of y uppercase of t, it is going to be y lowercase of x. And the right hand side is going to be c1 times e to -3t. So it is going to be e to -3 ln x. This is, it was t here. Plus c2e to 2t, which is 2 times t, right? Then this is a function in what? In x. Then if you recall what we have said before, this is e to -3 ln x. We can directly write it as exactly x to -3. And this is e to 2 ln x. It can be directly written as x to the power 2, right? So our final equation is going to be c1 times x to -3, which is said here, and c2 times x to the power 2, which is I have already said here. Okay, this is the solution for us for the case of x larger than 0. We're talking about x larger than 0. Okay, so this is the first example, and really it is illustrating what we have, the main idea of the Euler's equation. Okay, let's have another example and see how we can solve more and more examples using Euler equation. Now consider Euler equation as we have this equation: x squared y double prime minus 5xy prime plus 9y equals 0. We're going to transform, as you can see, this is really, it is Euler equation, even that they are saying that to us, but we can check it. X squared y double prime, there is no constants. We have x here, which is multiplied by y prime, and we have a constant, which is a, and plus constant times y, and the right hand side is 0. So this really qualifies to Euler equation form. Then we're going to make the transformation of variables, and we are going to transform it. So we're going to say that y capital double prime, this is, I think it's a mistake in the book, so it should be y double prime here every time, and this is y prime capital, okay, and this is going to be y only. Okay, so this is the equation, or the transformed equation. We have y double prime, y prime, and y. Here it is minus 6, because we have minus 5, so minus 5 minus 1 equals to minus 6. And this is b, which is the same here, which is b. Okay? With the general solution, then if you look to this, this is constant coefficient case, and the solution for it is going to be repeated roots with lambda 1 equals to lambda 2, and it equals to 3. Lambda 1 equals to lambda 2 equals to 3. Okay, so we have this repeated roots case. This means that our general solution for our parameter t with uppercase y equal to c1. So this means that we have c1 e first lambda, which is 3t, plus c2 times t times e raised to the power 3t. Right? So this is the equation that we have here. And then we are going to transform, remember well that this is for y of t after changing the variables, So now this t here and this t here, we're going to transform it to what exactly? Ln x, and here it is going to be ln x, right? This means that we have, now we can transform it. If we transform, we're going to find that y lowercase in terms of x as a variable, c1 e to 3 ln x plus c2 ln x, because we have t here, e to 3 ln x. This would end up as you remember, e to 3 ln x, it equals to exactly x cubed. Similar here, x cubed. And then ln x is the same, and c2 will be the same in this term. Okay, so this concludes the solution of our case, of our system. For x larger than 0, we are talking about x larger than 0. Do not worry about x less than 0. We can adjust it. So just if we could obtain the general solution for our x larger than 0, then for x less than 0, it will be adjusted with small modifications. So do not worry about x less than 0. Okay? So now this is the main idea for this example. Okay, now let's have another example and let's see how we are going to solve it. So we have here x squared y double prime plus 3xy prime plus 10y equal to 0. Seemingly it is Euler equation. X squared here, constant times x times y prime plus constant times y. Then we are okay. We have a equals 2, 3, we have b equals to 10. From here we can put our transformed equation. So the transformed equation is going to be y double prime plus, here it is a minus 1, which is 3 minus 1, which is 2, y prime plus 10, which is b, times y equal to 10. Take care, we're talking about y uppercase, which means that it is a function of the t, the transformed variable. Okay, with the general solution, this is constant coefficient case, and the general solution, it seems that you are going to find complex roots for your solution for this equation. The characteristic equation will be complex roots with the -1 and 3 for alpha and beta. So you can check this by yourself. So please, whenever that there is something, please check it by yourself and do it as your exercise for checking that the results are okay. Okay, and if there is anything, just let me know. So now our equation in this case, if we have the complex roots, if you remember, then the solution is going to be exactly c1 times e to minus t, which is lambda 1 here, cosine beta t, which is beta is 3, as I said here. So beta is 3, so we have alpha equal to -1, we have beta equal to 3, so we have beta here, 3t plus c2 e to minus alpha, which is t minus 1t times sine 3t. Okay, now this is the equation for t itself. Now we're going to transform it to our lowercase in terms of x variable. So we're going to change every t with ln x, as you can see here, ln x, and here ln x, which is inside the sinusoidal function. Okay, then we're going to have, if you remember, that e to minus ln x, equals to x to minus 1, as we said before. So this is pretty easy and straightforward. We're going to take 1 over x as a common factor, which is e to minus ln x, and then we're going to put the inside equation c1 cosine 3 ln x plus c2 sine 3 ln x. Okay, so this is another example that is going to make it for us regarding the Euler's equation and the form. Okay. Now, the last thing regarding this Euler equation is going to be the initial value problem. The initial value problem. We want to know how to solve initial value problem for Euler's equation. So as usual, we solve an initial value problem by finding the general solution first of the differential equation, and then using the initial conditions to determine the constant. That's the right thing. That if we want to solve an initial value problem, we are going to find some constants like C1, C2, and so on, right? So how to get rid of these constants? We're going to substitute with the initial conditions that we have in our problem. Okay, let's have an example and see. Solve x squared y double prime minus 5xy prime plus 10y equal to 0. As you can see, there is no constants here, and it's x squared. There is a constant here which is minus 5 times x times y prime, and there is a constant here which is 10. This is going to be our A, this is going to be our B. Okay, we want to solve this equation for the initial value problem, initial conditions, y of 1 equal to 4 and y prime of 1 equal to minus 6. So this is what we are going to solve. This is what we are going to solve. Then directly our Euler equation transforms to exactly y double prime minus 6, because we have here minus 5, so minus 5 minus 1 equal to minus 6, y prime plus 10, it is the same here, equal to 0. With the general solution, this is the characteristic equation. It seems that we are going to have like complex roots with 3 for alpha and beta. It is going to be 1, right? So we can check it, and we are going to have the general solution for the t parameter based on the uppercase y. It is c1e to 3t cosine t plus c2e to 3t sine t. Okay, so this is our equation based on t. Then we are going to replace, remember that we're talking about x larger than 0. Then we're going to replace this or transform the parameters to get the x variable. So the lowercase y with x variable, after substitution, we're going to have x cubed. Remember well that we have e to 3t. So this e to 3t, sorry, e to 3t means that e to 3 ln x. And this means that it is going to be x to the power 3, which is already we are having here. Okay. And then c1, it is the same cosine ln x, cosine t. c2 sine ln x, it is the same. X already cubed taken as a common factor. Now we can see that we have what? c1 and c2. They are the constants. We need to get them. Then we are going to use our initial values or the boundary conditions that we have. The boundary conditions. So let's go. Okay, let's go to this again. Our boundary conditions. I'm going to raise this again. Yes, our boundary condition we have at y equal to 1. It is at x equal to 1. Y of 1 equal to 4, y prime of 1 equal to minus 6. So we are going to substitute here. So y of x means that y of 1 equal to 4. So y of 1 equal to 4. And then the right hand side, if you see ln x, which is going to be ln 1, and this is ln 1 as well. So we are going to find that one of them is going to be 0 and the other is going to be 1. And we are going to end up with this c2 is going to be cancelled. It is going to be 0. And we are going to have this to be 1 here. c1 times x cubed. X cubed already it is going to be 1 because it is in the initial conditions. then this means that C1 is going to be 4. So we have obtained the first constant here, which is C1. So C1 equals to 4. This is the first constant to obtain. Let's still, we do not know C2. Let's go to the next. So for we have y of x equal to C1, which is 4, already we have obtained, x cubed cosine ln x plus C2, which we do not know, x cubed sine ln x. We're going to take the first derivative of this equation, y prime of x. So the first derivative is going to be 12x squared cosine ln x minus 4. Okay, because we have here like two equations, okay, sorry, two functions, x and the cosine, the x cubed and the sinusoidal function. So they are two functions multiplied together. Then we are going to putting the rule for the derivation would put 4 terms for us. 2 for the first term and another 2 for the second term, as you can see. The second 2 terms is going to be function in C2. However, the first 2 terms, they are going to be, yes, exactly, like as if they are having values. So we're going to substitute based on our initial condition. We said that y prime of 1 equals to minus 6. So we're going to substitute with x equal to 1, and we equate it with minus 6. You are going to find that C2 is we are going to end up with this equation, which is that giving us C2 equal to minus 18. So the solution of the initial value problem is here C1, which is 4, and here, which was, if we go back, which is C2, it is minus, this is C2, which is minus 18, and then this is our solution. This is the general solution of our initial value problem. General solution for our general, okay, the general solution for initial value problem. Okay, now I think that you are ready now to do anything and to do your homework, okay, home assignment regarding this issue. Okay, so our home assignment for you, we have like these initial value problems that I was talking about. So we have x squared y double prime plus 5xy prime minus 21y equal to 0, and we have these initial conditions. Okay, y of 2 equal 1 and y prime of 2 equal 0, and we have another one also here, x squared. So this is like homework number, this is problem number 1, for example, this is problem number 2, and still there is another problem in the next slide. So we have x squared y double prime minus x y prime equal to 0. Okay, and take care here that we do not have the y, and take care that our b is going to be 0, something like this. You check it by yourself. Y of 2 equal to 5 and y prime of 2 equal to 8. Then you can solve for this, and you can solve also for this. The third one, it is also another initial value problem. You can deal x squared y double prime minus 3xy prime plus 4y equal to 0. Very common for us to use the Euler's equation, and then the initial conditions are given here. So solve for obtaining the constants that needed for our general solution. Okay, so I think that I hope that by this equation or by this home assignment you are pretty familiar with the meaning of Euler differential equation and the form that you are going to use always to solve your equation, and how to make the transformation of variables, and how to solve for the constant coefficient linear second order homogeneous equation, and then transform back to your original x parameter and solve for the general solution. Okay, thank you for listening, and I hope that you understand this this Euler equation, this video very well, and see you in the next video.